Hi and welcome back to the course on Econometric Modelling. This is module 28 and 28 basically covers or start discussing the last topic under the univariate time series modelling. Here I am going to deal with modelling trend and seasonal variations. So, two modules would be dedicated to the discussion on trends and seasonal variations. The first one, that is module 28, specifically deals with trends, and in the second module we will discuss other seasonal variations. Now, time trends I already have actually introduced once while discussing something else. No, this is a very common thing, and what basically it measures is probably pretty easy to understand, but nevertheless a basic discussion is here that many economic time series have a tendency to grow over a period of time. This could be because of slowly evolving preferences, technologies, demographics, etc. This is known as trend or time trend. So, when something is growing irrespective of the impact of other variables or factors, and this is because probably of a time factor, then we can model it by using a time trend. While trying to draw causal inference using time series data, ignoring the fact that two sequences are trending in the same or opposite directions can lead us to falsely conclude that changes in one variable are actually caused by changes in another variable. In many cases, two time series processes appear to be correlated only because they are both trending over time for reasons related to other unobserved factors, right. For example, by this we simply want to mean that this is possible that there is an y series and there is an x series. One of them is increasing, the other one is decreasing monotonically. Alternatively, it is also possible that both y and x are growing over a period of time. Now, we can observe or expect some correlation between them, and the correlation would be obvious because when one is growing, the other one is also growing. But it is quite possible that they are completely unrelated to each other, and even if we observe a high correlation, it is not possible that they are actually correlated, right. Here we will focus on deterministic trends. Deterministic trends are trends that evolve in a perfectly predictable way. So far we have talked about random variables. The opposite of something being random is being deterministic. So, which can be determined with 100% accuracy is called deterministic. So, when you talk about deterministic trend, then we certainly want to imply that this trend does not involve any stochastic component. If we are incorporating a deterministic trend, then it implies that this trend is constant over a period of time. The trend is having an impact on the variable. If the trend is found to be significant, then it is having an impact on the variable concerned or the variable we are concerned with 100% accuracy. So, the trend part we can predict with 100% accuracy. So, if a variable is observed to grow over a period of time, and if inclusion of a trend explains nearly 99% of its variations, then it implies that we can predict the variable with almost 99% accuracy just by making it dependent on time, or the forecasts are much more easier. So, today the value of that series is say 100, and we have observed that it has been growing at a rate of 1% over a period of time. So, we could say that in the next period it is going to be 101. So, that prediction is there with a lot of determinism, and that is why we call it deterministic trend. One popular formulation to model trend is to write the series yt as yt equals alpha naught plus alpha 1t plus ut. This is basically the most commonly used expression for inclusion of trend terms into a regression analysis, where t takes the value 1, 2, 3, 4 and so on. So, if there are say 40 observations, then I have the last value of t at 40, where our error term I assume it to be well behaved. So, it is again a white noise process. It is identically and independently distributed with 0 mean and constant variance at sigma square e and sigma square e, or it can be sigma square u. and this is identically and independently distributed itself implies that there is no auto covariances or auto correlations between the values of the error term. The variable t is called a time trend or time indicator or time dummy. It takes the value 1 in the first period of the sample, 2 in the second period, and so on. The slope alpha 1 has the usual interpretation that holding all other factors constant, alpha 1 measures the change in y t from one period to the next due to passage of time, right. Now, in this expression we do not have any independent variable. So, this is we are actually focusing only on time and considering a time trend in as the factor responsible for explaining variations in y. Now, if I can write y t equals alpha naught plus alpha 1 t plus u t, then I must be able to also write at, and this expression is valid for all t, right. So, this must be the case that y t minus 1 is alpha naught plus alpha 1 t minus 1 plus u t, right. Now, when I consider delta y t is simply y t minus y t minus 1. So, what I have alpha naught plus alpha 1 t plus u t, this is the expression for y t, minus alpha naught minus alpha 1 t minus 1 minus u t minus 1. So, alpha naught cancels out, then this minus alpha naught t and plus alpha naught t, they also cancels out. So, I have alpha 1 minus plus alpha 1 plus delta u t, and delta u t is u t minus 1, which actually considers all other variables explaining variations in y t. So, if we can assume that all other things are constant, so delta u t is equals to 0, then I will be having delta y t equals to alpha 1, right. So, this is the interpretation of alpha 1, that it actually measures the change in y t from one period to the next due to simply passage of time, right. Another way to think about a sequence that has a linear time trend is that the average value is a linear function of time. So, if we take the expected value of this expression, then we would be arrive at this expected value of y t equals alpha naught plus alpha 1 t. These are constant terms, right. So, the expected values are same, and expected value of u t is equals to 0. So, this is what is the expected value. If alpha 1 is greater than 0, then on average y t is growing over time and therefore has an upward trend. We say that y t has an upward trend. If alpha 1 is less than 0, then y t has a downward trend. It is actually a downward sloping line. The variance of y t is constant across time, because as you can see that alpha naught and alpha 1 t all are deterministic components. They do not change over a period of time, and that is why their variances are 0. So, variance of y t is actually equal to variance of u t, and variance of u t, if it is equal to sigma square E, then that is also equal to variance of y t. Sometimes trend appears non-linear or curved. As for example, when a variable increases at an increasing or decreasing rate, then we actually cannot use a linear trend. So, the simplest form and the most popular form is linear trend, but trend need not be always linear. So, in that case we do not require the trends to be linear. What we want is that the trend to be smooth, and as a result of which we can also consider non-linear trends. So, one kind of non-linear trend is quadratic trends. We can allow for gentle curvature by including not only t but also t square, such that my original equation, which was y t equals alpha naught plus alpha 1 t u, becomes this, where we have added one alpha 2 t raised to the power 2 or t square plus u t usual, and u t is again IIT, that is identically and independently distributed with 0 mean and constant variance equal to sigma square. This is called a quadratic trend because as you can see that the trend is a quadratic function of time. Linear trend emerges as a special case when alpha 2 is equals to 0. So, if we set alpha 2 equals to 0 or if we find the quadratic trend to be insignificant, then of course it will be a linear trend. Understandably, a variety of different nonlinear quadratic trend shapes are possible depending on the signs and sizes of the coefficients. For example, when both alpha 1 and alpha 2 are greater than 0, the trend is monotonically but non-linearly increasing. So, I will be having pictures or graphs of monotonically but non-linearly increasing trends, quadratic trends. Similarly, when alpha 1 and alpha 2 both are less than 0, the trend is monotonically but non-linearly decreasing. If alpha 1 less than 0, alpha 2 greater than 0, the trend has a U-shaped curve, and when alpha 1 is greater than 0 and alpha 2 is less than 0, the trend has an inverted U shape. So, this is what we are showing here with examples, that in panel A, this is panel A where we have both coefficients positive. So, we have a monotonically increasing quadratic trend. In panel B, we have one positive, one negative. So, this is panel B. So, this is an inverted U-shaped trend. Panel C has both negative coefficients, and that is how we have monotonically decreasing trend. And finally, when we have a negative coefficient for t and a positive coefficient for the quadratic term t square, then we have an U-shaped time trend. Okay. So, quadratic trend actually is more useful from the perspective that if we plot a series and actually plot a series against time and we do not see it to be much linear, then quadratic plots can be, or quadratic trends can be of much help. That will give us a better fit of the model. Without considering any explanatory variable, a quadratic trend may explain a major part of the variations in our dependent variable. Another type of nonlinear trend is exponential trend, but this is again a very popular and common trend that we often use in economics, and this is popular also because this can be converted into linear form. So, many economic time series are better approximated by an exponential trend or log linear trend we call it, which follows when a series has the same average growth rate from period to period. Exponential trend is common because economic variables often display roughly constant real growth rates. So, if we observe that the real GDP of an economy has been growing for the last 10 years at a rate of 2% per annum, then this can be probably plotted as an exponential trend. In practice, an exponential trend in a time series is captured by modeling in natural logarithm of the series as a linear trend, and in order to consider natural logarithm, we must have yt greater than 0, as you know that we cannot have logarithm of negative values. So, provided that the series takes only positive values, we can go for a natural logarithm. So, in case most often if we are working already with growth rates, for example inflation can be positive as well as negative. So, in that case we may not work with an or we may not consider an exponential trend. But for most other series, for example GDP in its absolute values, either real or nominal, can be always considered for an exponential trend model. So, if yt or when yt is greater than 0, we can go for an exponential trend, and it is written as log yt equals alpha naught plus alpha 1 t plus ut. You can see that the right hand term remains the same like that of a linear trend. We call it a log linear trend because, or log linear model, because we have logarithm on the left hand side and but the right hand side is in a linear form, and it is a log linear trend because this model actually trying to incorporate a trend term. Exponentiating equation 1 shows that yt itself has an exponential trend. So, yt is actually can be written as exponential alpha naught plus alpha 1 t plus ut. Since for small changes we know that logarithm of yt, for small changes in logarithm of yt, that is delta log yt equals log yt minus log yt minus 1 is approximated by the proportionate change in yt or growth in yt. So, what we are trying to say is that this delta log yt is actually approximately equal to this proportionate change in yt for small changes. Then it follows that taking changes in equation 1 and setting delta ut equals to 0. This was our equation 1. So, setting changes in equation 1 and setting delta ut equals to 0 gives us delta log yt equals alpha 1. So, earlier what we had is that delta yt, when we are considering a linear trend, now look at the difference. When we are considering a linear trend, then our delta yt was equals to alpha 1. When we are considering an exponential trend, then delta log yt is equals to alpha 1. And what does it imply? Delta log yt is actually not equal to delta yt. Delta log yt is equal to growth rate in yt, approximately equal to growth rate in yt. So, here if we are going for an exponential trend, then alpha 1 measures the constant change in the dependent variable, right, constant growth in the dependent variable. So, what it says is that with time the series is growing at a constant rate, and what is that constant rate? The rate is alpha 1. Linear or non-linear, we must be careful to allow for the fact that unobserved trending factors that affect yt might also be correlated with explanatory variables. If we ignore this possibility, we may find a spurious relationship between yt and one or more explanatory variables. This phenomenon of finding a relationship between two or more trending variables simply because each is growing over time is an example of a spurious regression problem. Fortunately, adding a time trend eliminates this problem. So, it is possible that independent variables and dependent variables both are functions of time trend. Both have some components which actually, or both are growing just because they are growing with time and they are actually not related with each other. This problem has also been probably discussed in the beginning of this module, that if it is possible that they are unrelated and we observe relationship between them just because both of them are growing over a period of time. Now, if actually they are unrelated but we observe a relationship between them by running a regression, then we call it a spurious regression, right. And this problem can be considered or tackled by simply including a time trend into the regression analysis. That will take care of any trend component that might be impacting the independent as well as the dependent variables. So, we now take an example. The following figure plots CPI combined from India for the period 2016-17 April, these are monthly figures, to 2020-21 July with the base period 2012. So, we have actually plotted one linear trend and one quadratic trend. These are simply generated by taking the data into Excel and the graphs are plotted, the trend lines are added, right. You can see that the linear trend actually is quite a good fit. And when we go for quadratic trend, the curvature is actually very small or minute. One can also ignore such a curvature. The linear trend in itself is quite a good fit. So, when you go for estimation of the series, what we do is, first of all, for linear trend we have CPIT, the dependent variable, and this is a linear trend alpha naught plus alpha 1t plus ut. And alternatively, I have considered one quadratic trend where CPIT equals alpha naught plus alpha 1t plus alpha 2t square plus ut. The data remains the same. So, the following table compares the estimates of two alternative models of linear and quadratic trends of CPI combined data from India for the period 2016-17 April to 2020-21 July with base period 2012, and there are 52 observations. So, if there are 52 observations, you can understand that the degrees of freedom for this model will be 50 and the degrees of freedom for this model would be specifically the residual degrees of freedom for this is 50 and the residual degrees of freedom for this model is 49. This is 52 minus 3, this is 52 minus 2, there are only 2 variables. Now, looking at the estimates, we see that alpha naught is given as 126.55 here, 128.90 here, both of them are highly significant, it has huge t values. Then alpha 1, actually all the variables are or all the parameter estimates, I can denote them by alpha naught hat, alpha 1 hat. So, all the estimated parameters are significant at 1% level of significance. So, that is not a worry. The t statistics are measured in the parenthesis. Okay. So, in the parenthesis or in brackets we have the t statistic. But what we observe is that when we just have a linear trend, the linear trend explains 0.46% of the variations in the dependent variable, that is the CPI combined series. So, what it says is that as time changes or with time, when you move from 1 month to the next month, CPI increases by 0.46. The R square value is 95%, adjusted R square is also 95%, which implies that 95% of the variations in the dependent variable is explained. And when we consider the quadratic trend, what we observe is that alpha naught is again a big value, alpha 1 has slightly come down now, but this is still significant, it is now 0.21, and alpha 2, the coefficient of the quadratic term is very small, but it is also significant, it is 0.005. I have mentioned here only up to 3 decimal points, because otherwise for 2 decimal points it would have been simply 00. So, the quadratic term, though significant statistically, is actually not much perceptible. The impact is or probably the shape or the contribution of the quadratic term is very small to the dependent variable. R squared value as well as adjusted R square value has also increased. Inclusion of the quadratic term, since it is significant, explains 97% of the variations in the dependent variable, that is CPI combined. Now, we talk about detrending a time series, how we can remove the trend component of a time series. Either we can incorporate a trend, or we can also work with detrended series. Now, this is actually not important, in the sense we do not need to detrend a model or detrend a series, but what it shows is that if we go for detrending a series, then and if we work with detrended series, then we are actually going to get back the exact same estimators if we would have included a trend in the original model. So, suppose this is my original model where yt equals beta naught plus beta 1 xt1 plus beta 2 xt2 plus beta 3 t plus ut. So, I have considered 2 independent variables, there can be k independent variables. The procedure to detrend a time series is to run a regression of the series on a constant and the time trend. So, you run a regression on the constant and the time trend, collect the residuals which constitute the dependent variable without the trend term. For example, regress each of yt, xt1 and xt2 on a constant term and the time trend t, and save the residuals, and we are calling these residuals, we can call it simply the residuals obtained from here, which is ut hat, vt hat and wt hat. Now, one thing I would like to note you here is that this ut hat is different from the ut here, right, because the equations are different. This is just for the sake of notational purpose, I have mentioned ut here. One can also call it et, so that the problem of confusing this ut with this ut does not arise. But suppose I am denoting the residuals obtained is yt tilde, xt1 tilde and xt2 tilde. Why I am denoting it like them? Because in the next step, what I am going to do is that regress this residual on these independent variables. Now, the point is that if these variables do not have any trend term, or any variable does not have a trend term, then the trend term will be insignificant, and this residual and this one will not differ much. But in case there is a trend term, this trend term will be eliminated. Now, y t tilde is a series which is the original series except for the impact of the trend factor. Similarly, x t 1 tilde is the original series without the impact of the trend factor, and x t 2 tilde is again the original series without the impact of the trend term or trend factor. Now, if we run a regression of y t tilde on x t 1 tilde and x t 2 tilde, then the regression exactly yields beta 1 hat and beta 2 hat from equation 2. So, this is my equation 2. If I would have estimated this equation and obtained beta 1 hat and beta 2 hat, they would have been exactly equal to from a regression of y t tilde on x t 1 tilde and x t 2 tilde. This means that the estimates of primary interest beta 1 hat and beta 2 hat can be interpreted as coming from a regression without a time trend, but where we first detrend the dependent variable and all other independent variables. The same conclusion holds with any number of independent variables, and if the trend is quadratic or of some other polynomial degree. So, in a similar fashion, we can detrend any series having quadratic trend or trend of any other polynomial series. If the trend term is statistically significant, the results change in important ways when a time trend is added to a regression. Then the initial results without a trend should be treated with suspicion, which implies that a significant trend term, if the trend is significant, then it must be included into the regression analysis. Otherwise, my regression results might not be valid, because simply because of the reason that an important variable has been dropped from the equation. Also, it is possible that I am estimating an equation like y t equals alpha plus x t plus ut. Now, this is possible that y t depends on a trend term and x t also has a trend component. Now, when t is not included here, then t goes into the error term, and if x t also has a trend component, then x t and ut will be correlated with each other, and as a result of which my CLRM assumptions will be violated. The regression results do not fulfill the Gauss Markov or CLRM assumptions. My results are not actually trustworthy. They cannot be dependent upon, they are not reliable results, right. As a result of which we are saying that if the trend term is significant, they must be included into the regression analysis. So, that is all about inclusion of trends in a regression analysis, the possible forms, their impact, and how we can go for detrending. In the next module on trend and modeling seasonality, I will be dealing with other types of seasonality or other seasonal variations that we experience in the time series, economic and business time series. Thank you.